Have you ever stopped to wonder what's really going on under the hood with something like ChatGPT or Midjourney? Well, today we're cutting through all the hype. We're going straight to the source, the actual research papers, to give you a clear, no-nonsense look at how this technology really truly works. I mean, that's the big question, isn't it? How on earth does a computer, a thing of logic and code, produce something that feels creative, something that feels like us? That's the mystery we're going to unravel right now. All right, let's get a key term down first. The AIs that power things like ChatGPT are called large language models, or LLMs for short. Now, they're part of a bigger field called natural language processing, but what makes them special, what makes them revolutionary, is their incredible scale. We're talking about models trained on a mind-boggling amount of text, and that massive scale is exactly what gives them their power and flexibility. So, here's our game plan. We'll start with what these LLMs are, then we'll dive into the transformer architecture that made them possible. We'll look at why making them bigger was such a game changer, and then we'll switch gears to see how AI creates images using diffusion. And of course, we have to talk about the limitations before we look at what's next. Okay, so we've got these giant models that can understand and write human language. But what was the breakthrough that made them possible in the first place? To get that, we need to look at the engine that makes them go. And to really get how today's AIs work, we have to jump in the time machine and go back to 2017. Because that was the year a single research paper landed that completely changed the game for AI development. And here it is. This is the paper that kicked everything off. Attention is all you need. It came from a team at Google, and it introduced a totally new design called the transformer. And that architecture, it became the foundation for basically every major generative AI model that followed. This line right here, from the paper's introduction, tells you everything. The two most important words are simple and solely on attention. They were basically throwing out the old, complicated rulebook and proposing a much more elegant, streamlined approach. And this chart shows you the difference perfectly. See, before the transformer, models had to read text one word at a time, in sequence. Imagine trying to understand a story that way. You'd easily lose the context. The transformer, with its attention mechanism, could look at the entire sentence all at once. It could weigh how important every single word was to every other word, all at the same time. And the results were immediate. The quality on things like language translation just shot through the roof. But the real game changer was that this new design was parallelizable. That's a technical term, but it means you could train it on tons of computer chips, GPUs, all at once. This slashed training time, and more importantly, it made it possible to build models at a size and scale nobody had ever dreamed of. And that unlocked the next big piece of the puzzle. So you've got this new, super efficient architecture. The next question for researchers was pretty obvious. What happens if we just make it bigger? I mean, much, much bigger. And that question got its answer in 2020. With this paper from OpenAI. It's called Scaling Laws for Neural Language Models. And this is the research that basically gave everyone the recipe for the AI explosion we're seeing right now. What these researchers found was just incredible. A model's performance wasn't some random accident. It actually got better in a predictable way, following something called a power law, based on 3 specific things you can increase. Suddenly, building AI became less of a guessing game and more like an engineering discipline. First up, and this is the one you hear about most, is the size of the model itself. This is about the number of parameters in the model. You can think of them like little knobs that get tuned during training. The more knobs you have, the more complex patterns the model can learn. The second ingredient is the size of the dataset. You can have the world's biggest engine, but it's useless without fuel. The model needs a gigantic library of text, books, articles, websites to learn from. The more it reads, the more it understands. And the third factor that ties it all together is compute. We're talking about pure computational horsepower. Thousands of GPUs running nonstop for weeks or even months to train these huge models on those massive data sets. The paper showed that when you increase all 3 of these things together, you get these amazing new abilities. But here's the kicker, the really counterintuitive part from their research. It turns out bigger models are actually smarter learners. They learn faster, they need to see fewer examples to get to the same level of performance as a smaller model. So if you've got a limited amount of computing power, the most efficient thing to do is to train one very large model. That insight changed everything. Okay, so we've covered how text gets generated, but what about all those incredible AI images? Well, that's a completely different approach, a different technology that grew up on its own parallel track. Let's dive into the wild world of diffusion models. Just like attention is all you need was the big bang for LLMs, this 2020 paper was the landmark moment for image generation. It laid out this really powerful and practical way to create the super detailed images that we're all used to seeing now. So how does it work? Well, the main idea is actually surprisingly beautiful. You train a model to do just one thing. Take a slightly noisy image and make it a tiny bit less noisy. And by getting exceptionally good at that one simple task, it learns how to reverse the entire process of a clean image dissolving into static. This breaks it down perfectly. The whole process starts with nothing but pure chaos, a screen of random static, like an old TV with no signal. Then, using your text prompt as a guide, like a photo of a cat in a library, it starts to remove the noise, bit by bit. With every single step, it refines the image, pulling a structure out of the randomness, until finally, a clear picture emerges. Now, these technologies are obviously incredibly powerful, but we have to do a reality check. It is absolutely crucial to understand that they are not perfect. They come with a whole host of challenges and limitations that researchers are working hard to solve. For one thing, because these models learn from a snapshot of the internet, they can pick up and even amplify the biases that are already in that data. Then there's the problem of factual inaccuracies. People call them hallucinations, where the AI will just state something that's wrong with total confidence. And maybe the biggest challenge of all is that we're still figuring out why these models say what they say. Their inner workings are still a bit of a black box. And all of this brings us to the future. For the last few years, the mantra in AI has been, scale is all you need. Just build bigger models and you'll get better results. But now that conversation is starting to shift. People are asking, are we hitting a wall with that approach? This quote about Matthew Kerrigan, one of the experts behind the Hugging Face course, captures that feeling perfectly. The thinking is that just making the transformer architecture we have today bigger and bigger probably isn't going to be enough to get us to true artificial general intelligence. It suggests we might need another fundamental breakthrough, a whole new idea. And that leaves us with the big, open question hanging over the entire field. We've seen how the transformer unlocked text generation through scale. We've seen how diffusion models unlocked image generation through denoising. But if scale alone isn't the final answer, what's next? What is the next attention is all you need that will push all of this to the next level? That is the question that researchers are trying to answer right now.